But since pluralism covers amplification and all the rest, we covered OSNR, we covered amplification. Byron also covered that amplification also amplifies noise. It just doesn't amplify your signal. Because before I explain DSP, I think we need to touch on effect. We have looked at all the components that causes errors. What was the first one? Attenuation, already covered, fiber loss. What else? We looked at dispersion. We looked at chromatic dispersion, which is light traveling at different speed. There is also, once you start sending different polarizations, there is also dispersion cost because of that. Because the two polarizations may not be at the same time. One polarization might be earlier. You again cause broadening, again causes errors. So what do? We need to find a way to correct that. Right? So that's where we have forward error correction. I generated this with ChatGPT, just to get some concepts here into what forward error correction is. Being from a telco background, remember those days of ISD calls where you're trying to speak on a very cranky line, noisy line? And when things are not clear, the receiver keeps telling you, can you please repeat whatever you say? That's what actually happens when you're trying to build a link. So, yes. So in fact, what do is we agree on a quorum, right? We say like, hey, if it's something important, maybe give me extra hints, paraphrase it, so that you don't have to keep asking me to keep repeating myself. So that's what FEC actually does. If I repeat or paraphrase certain important parts clear enough, you as the other end, even though it's a noisy line, you're able to make sense of what I was trying to say. So that's what forward error correction actually does. I leave enough hints in the information when I translate it to you that even if there are errors, you extract those hints out and then you're able to correct the errors that you receive. Right? So that's what FEC is at a very high abstract level. Right? Because again, I'm trying to say this purely from an IP point of view. The reason why I'm going here is once you go IP over DWDM and the rest, once you see this telemetry, you need to be able to understand what it means. Right? So FEC is one thing that you will see on your router or switch CLI. It's a telemetry that you will have to collect. Right? But in reality, what it means is with forward error correction, it means it allows me to work with a lower OSNR. I can correct errors, even if there is low OSNR, because of which there are errors. Thanks to FEC, I'm able to correct those errors. What does that mean? That means I'm able to either extend my reach or work with a bigger margin on a bad quality link. It doesn't improve your link. Many people think FEC does magic on your link. A bad link is still a bad link. What FEC tries to do is it tries to avoid retransmissions, it tries to correct the errors. That concept of no free lunch still applies, right? Beyond, you can't let your OSNR drop to a level, where the error is so huge that FEC can't do corrections. So we tend to call that pre-FEC, pre-error correction with error rate. It needs to be at a certain, it needs to be maintained at a certain threshold, which means you need to maintain the OSNR at a certain threshold so that you can achieve that bit error rate at that threshold. If it drops below that, your OSNR, there's no magic. FEC can't do anything. So don't think that, oh, with FEC, any bad quality link is a workable link. FEC can only do so much. Right? Putting all those concepts in, we have the DSP. Remember earlier when I was trying to show how a coherent receiver works? If I can find my slide. There is the coherent receiver. There you go. Right. Remember we discussed this? Your coherent signal comes in, I have a local oscillator, a local laser on the transceiver, which actually then mix coherently, you extract amplitude, phase per polarization, and you feed it off to the DSP, the digital signal processor. And what the DSP does is magic. Right? So it's responsible for all your encoding, decoding of your signals onto the carrier wave, right? So you do all the encoding into amplitude, phase, and polarization. Remember, I also mentioned something about pilot signal insertion. Because now we're using phase, amplitude, polarization, you need some way to signal to the receiver. You need to give the receiver some reference point. And that reference point is what we call a pilot signal. That I insert at the TX so that the receiver using that reference point then starts extracting the phase and amplitude per polarization. So that is done, again, you don't have to do it, the DSP does it, right? FEC is also a DSP function. Byron touched on this. In the old days, we had to have DCM modules, dispersion compensation modules, and sometimes you overcompensate. What do you do when you overcompensate? You keep adding, so this is a real story. We overcompensated. I don't know how, we were all new young engineers. We didn't know how to do our design well. The DCM module that ended up, we were buying packet like those days. Israeli shipped it to us. It was overcompensated. The only way we could do was add another 100 kilometers of fiber. So you can see that from our server room through the window, we had to dig holes, send it out. We had a drum, 100-kilometer drum outside just to make sure that overcompensation can be corrected. But now no need to do that because your DSP does it. DSP does it for you. So that's why the old fibers are now getting a new lease of life. In the old days, we said, oh, this are bad. But now with coherent receivers and with coherent signal, because the DSP does all the magic, those fibers are now. And actually, coherent plays well when there is dispersion on the link. So that's why, so your DSP does that. And there's also a relatively new concept called probabilistic shaping. That's on that. Which is again a DSP function. I don't do it. You just need to know the concept. You don't have to do anything. The DSP does that. Right? This is where we started. So it already existed. That DSP thing, transponders were already doing it, but they were big. Discrete components, we have silicon photonics, photonic integrated circuits, and Moore's law applies. Now we even have 3 nanometer DSPs. From 28 nanometer down to 7 nanometer. The first ones that we built were 7 nanometer ones, then 5 nanometer, and now we are building with 3 nanometer DSPs. So that miniaturization technique is. I'm all over it.
The amount of dispersion that your traditional line card design coherent module could do versus the transceiver. Is there a significant difference?
Yes, there is, based on, because the DSP, how I go crazy with the DSP depends on how much power. DSP consumes a lot of power. If you look at your transceivers, and if you look at the TX power is what? 0.001 watts or 0.0001 watt. 99% of the power is lost because it's consumed by the DSP and it's lost at sea. So on pluggable transceivers, because I am limited not by what my transceiver consumes, but by what the switch or the router ports allows me to consume. Because remember, our routers and switch ports are used to 3 watts, 2 watts, 5 watts consumption. All of a sudden, I need 30 watts, 23 watts. So how many ports do I pack? So you're right, the DSPs on the pluggable transceivers still can't go crazy. It is capable if that thermal limit did not exist. But because of the thermal limit, and if it's just 1 port, who cares? But if I want to load 96 ports on the switch or a 32 port on the switch, then I do have to care.
Right, I think it's important to say this, right? Any optic, if it's a local optic on a transceiver or a transponder or it's a pluggable, about 80% of its power draw is heat. It's, optics are very efficient heaters. They're very bad at converting electricity into photons, but they're very good at converting it into heat. So especially WDM systems are very big heaters.
So if you look at a typical 400 gig ZR, what is the TX power? The launch power is what, minus 10 dBm. But it consumes about 19 watts, just one plug. So that's 19 watt on one switch port or on one router port. And like Byron said, minus 10 dBm is not much power actually, it's 0.1 milliwatts. Where did the 18.9999 watt go? It was consumed by the DSP and thrown out as a heat. So that was a really good question. That's why, although IP over DWDM is doable, I think we also need to apply common sense and say, is every link or every path pluggable? May not be, right? There might be some links where I really need aggressive DSPs, I really need aggressive algorithms, and not the right place to do. You might need to go with embeddeds, you might need to go with transformers, because they don't have that thermal cap that a pluggable might have, because the pluggable's biggest problem is it goes into routers and switches.
Yeah, and it's limited by the amount of power that the QSFP envelope allows it, right? Which is a set limit on any device. So some devices you'll see the cases, sorry, Tashi, for joining in.
Yeah.
But in some cases you'll see it's yet again, it's no free lunches, right? So you'll see that some vendors, that's when you go IP over WDM, they will tell you, listen, you can do coherent optics on this device, but you cannot fully populate the cages. The QSFP cages can do every second interface up to 8.
Power supply.
Yeah, because the backplane power supply is the limitation. Some guys build them to have enough juice, but you're still limited by the QSFP or QSFP DD standard, because they limit the power envelope to a certain amount of wattage. So QSFP 28, I think the wattage limitation or envelope is 5 watts, 6 watts, and then QSFP DD is 14 watts upwards. And better processing requires more power.
And it's not just your port derating that alternate port. Your PSU of the router or the switch, you're not do it. So you might actually need to go and look at your vendor documentation and go, what is their recommendation? Use this if you're using 1 gray, but the moment we plug in coherent, they might say this PSU is not going to work, replace the PSU. All seem interesting. You might need to go with a 3 kilowatt PSU or a 4 kilowatt PSU. All of a sudden, now we're talking our routers consuming, our switches consuming in kilowatts. In the old days, even if I have 48 ports, 2 watts, 3 watts per port. Beautiful. Now all of a sudden, if you go with 800 gig OSFPs, 30 watts per port. And imagine if it's one thing for it to consume it at one go, but what if it's running at full capacity the whole time, coherent? So you need to think of it not just from an initial fill, but also it's running on full load the whole time. And then you factor in the cooling aspects. And for that cooling, you factor in extra power required for that extra cooling. So
you'll actually start seeing in the industry also to get rid of the heat, especially in high density systems, you'll get some QSFP DDs that have like on board heat sink. So your pluggable will be slightly extended and it will have like a front end heat sink. Because yet again, optics are very good heaters.
So you start seeing all those fins on that, right?
There's a bit to do on the OSFPs, especially the 2 types.
Okay, to continue. Yeah, since I mentioned your DSP does PCS, again, very abstract. This is not deep. Technically, it may not be accurate, but the concept is right. Traditional comm, remember what I said? How far is a signal from the origin is how much power I need to transmit that signal. With our traditional comm, what happens is the probability of me using the inner low power points versus the outer high power points are the same. Right. So what PCS does is a little bit of magic. It says, let's use the inner points more often, low power, and use the outer points less often. Right. And it makes a lot of difference in terms of how much power is the requirement, which means I can now either buy because I consume less power. And so PCS, these are some magics that really have been happening thanks to DSP technology. Right. The reason I am touching on this is because the next slide is a screenshot. Remember, we started off with disaggregation, open standards, OIF, MSA, all the open standards and disaggregation, where you are now able to use plug from one vendor, open line system from any other vendor, mix and match based on your preference. And we also state now the form factors are very router-friendly, switch-friendly. So it's, okay, fine, I'm able to plug it into my router, I'm able to plug it into my switch, but can they talk to each other? And talking is fine. I might say, all right, it's on, it's up, but if it can't manage or control the transceiver, the host needs to be able to, whatever you plug into the host, be it your router or switch, I need to be able to manage and control it. If the distance is short, maybe I'll go maximum capacity. If the distance is long, maybe I want to trade off capacity for reach. How do I do all this? That means your host needs to be able to talk to your plug so that the host is able to control and manage the plug. And there was no standard way of doing it until CMIS, and that's what Byron was covering earlier. So OIF came up with Common Management Interface. What it allows, again, from an IP point of view, is portability of the plug. Any plug from any vendor should be able to work on any router or switch. That's at least the principle. It doesn't should. Yeah, it's a very big should. Yeah. It's at least the principle with which we work, but it doesn't always happen. So you will need to figure it out once you plug it in, how it talks. And then later they added coherent part to it. Hence you will see CCMIS as the coherent common management interface. Again, the whole idea is, can a plug from one vendor work across any router or switch vendors that you have?
And there are, just to add on to it, there are big events every year, like OFC, yes. That where every optical vendor, every router vendor, WM vendors, they literally build a fully open system where one node is a Nokia node talking to an Atra node, talking to a Sienna node. And it's got on the one side, it's got a Juniper talking to a Rasta on another node, and it's got a plug from Flex Optics and a plug from Cisco, and you name it. So they do this massive workshop at OFC every year to literally do this and shape and define the standard a bit better.
There's some very good white papers on this year's plug test. From
yes. So I'll at the end of the presentations when we share them, we'll add some links on the OC stuff. It's good to know, yeah. And yet even testing how stuff is tested it becomes a part of that, right?
One example, right? At last year's OFC, that's when they first tried the 800 gig alien across open line system. The reason why I touched on that was because I wanted to show you this. All the concepts that we covered, finally you have a coherent plug, you plug it into your router or a switch. This is what you see on your router and switch. You now have real optical telemetry on your router and switch. But as IP guys, you need to be able to make sense of what these parameters mean. And automation, and that's where, right? You can, what you may not want to do on layer one or at the optical layer, you are still able to do certain things at the higher layers. I can automate a lot. I can do switchovers. I don't know. Again, back to my automation framework. I'm a big open config guy, gRPC, GNMI. If you use all those, I might be able to switch things, react things, reroute traffic as the threshold starts. As the parameters starts hitting my threshold, while my team investigates that, I should be able to reroute traffic across to other working units, right? But how do you do that without you understanding what is CD. Now you know it's chromatic dispersion, right? You know what OSNR
And
means.
it's just dispersions measured in picoseconds.
Yes,
It's complicated.
just for fun, right? 10
Picosecond,
power minus 12.
picoseconds per nanometer.
And like Baron touched upon it earlier, you should be able to estimate what the link is. On average, maybe 16 to 17 picoseconds per nanometer per kilometer, and this looks like what, I don't know, a 90 plus kilometer link or a 97 kilometer link. Right? So you're able to see all these things, and if I am now wearing my IP hat and my automation hats, I would start first collect them, normalize them in my, I don't know, whatever database you use, normalize them, and then you define your thresholds. On a good link, what is the threshold? Right? And based on whatever you read, and this is telemetry, but you don't want to always keep collecting, right? There are techniques you can use. Maybe I could do sampling. Right? Give me an average every 10 minutes. Instead of just throwing me, the optics throwing me everything, I could say, let me just sample it. Based on that sample, remember we discussed lower OSNR is bad because it causes higher bit errors. Right? But you don't want to just react because the OSNR is dropping.
What is a good OS in R?
How long is a piece of string? Right? So here is the challenge, right? Especially when we're talking about coherent optics. It is, what's the modulation rate?
Okay.
What's the bit error rate?
Okay.
What's the spectral width?
Not an easy answer.
It's impact. It's and also what is the PSD capacity, right? So if the PSD is unlimited in dispersion, so if on one of our cards, a 200 gig card, it will bring up a 200 gig 4-QAM service up at 18 dB, nothing lower, OSNR. And then the next generation of card that does it at 8-QAM, the OSNR looks totally different, the minimal OSNR. So it's your modulation and everything has an inherent impact. Yeah.
So that's where the multiple
Okay.
option comes, right? So if you administer the network, if the network runs on itself, I don't need engineers. Right? But if you are the person who is managing the network, you define, right? You can trade off. You can trade off capacity for reach. If I'm okay, and I'm like Baron mentioned, I don't want any inline amplifiers. I just want to keep pushing for that span. Maybe I need to compromise on the bit rate. I could go like, for that span, I'm okay to do 200 gig. Right? That means I rely on low order modulations, but you see all of a sudden my OSNR requirement is actually lower. Right? So for you to actually set what is the threshold, back to this one, is you need to actually know your network, you need to know every span. And that's why I think this tutorial is important, because with IP over DWDM, IP and optical folks need to work together. No more fiefdoms, territorial. Like it or not, things are converging.
That's exactly where I am now. That's exactly where I am now.
IT folks need to know optical concepts. Optical folks need to be able to work with IP folks to say, whatever, like the sub 50 millisecond switchover that we discussed.
Yeah.
Great, right? But can I also do that level of switchover through a high level automation? What if I already have segment routing deployed on my network? Any NPLS segment routing people here? Yeah, there you go. Segment routing will allow me to do a lot of things at upper layers. So can I combine this visibility, make a logical thing and go like, hey, if my OSNR plus my prefect blur, so you can take certain parameters, mix them and say, hey, if this drops and this drops and this also drops, something is eventuating until I investigate what that is to reroute my traffic. Right? I could use a segment routing. I could create an instruction set, say, route the traffic out that interface. Now your link is the interface. Once you plug in IP or DWDM onto your routers and switches, in the old days it might have been a link. But now it's from this interface, send it to that interface, the third interface, read out traffic across that while I investigate what is going on. But for us to be able to make sense, IP folks, to be able to make sense of this, we need to understand optical concepts. Not too deep, but enough to make sense. Make sense?
Yeah.
Right? And we already covered majority of this. And one thing I wanted to mention is the RH frequency. RX power is a thing. One thing about coherent that I wanted to mention, which I'll try to cover later, is coherent, remember, has a local oscillator. Coherent receiver, I see you have a local laser on the optics. And it only latches onto one frequency, which is what the TX10. That means I can take advantage of that, which I'll try to cover later as a wrap up. That's the beauty of coherent. In the old days, I need to scan, lock in, but now no more. With coherent, TX and the RX, they have already locked in because the coherent receiver can only talk on that frequency.
Specific for that frequency.
The word coherent, it comes from that. I need to be on the same frequency as you, and we need to have the same phase difference. Hence, why it's called coherent. I think this is the beauty, not anything else, right? The beauty is the fact that I can consolidate the management and control function for both IP and optical now into one. Right? You have this beautiful visibility that you get, which ideally you wouldn't get. If I'm getting a gray handover, I don't get much visibility to that. So generally the way IP folks react is once things start fading on the optical side. But with this level of visibility, if you have enough tool sets, you should be able to react. Right? And that was the ZR standards. And now you have multi-rate options in other standards. Problem with ZR is you're fixed, right? You can only do 400 gig, right? There's no compromise. You're stuck with one fixed modulation. You're stuck with all the thresholds are predefined. But with multi-rate options that you see in ZR Plus, 400 gig ZR Plus or 800 gig ZR Plus, you have this multi-rate option so that you can then, based on how your link looks like, based on your requirement, longer reach, compromise on this. If you're okay with the reach, go with the highest capacity that you have. So you can trade off between reach versus, but not every link is a pluggable link, I wouldn't, unless you run a hobby network. If you have a network where customers are there, if you have customers paying you, not every link is a pluggable link. So certain links you might need to apply judgment and say, hey, don't touch that, it's not a pluggable thing. But on majority of the links, you might be able to do IP over DWDM with plugins. And it's no more just labs, right? I was involved with ARNET, is Australia's oldest network. Australian Research and Education Network. They did the longest IP over DWDM tests. Australia is massive. It's a continent people forget. So it was from Sydney to Perth to Singapore, loop all the way back to Sydney. So it was about 4,600. So it's 2,300 kilometers one way. 4,600 kilometers. But it was using what Byron mentioned. It was using ultra long haul. The launch power is higher, the DSPs are more power hungry. It can go a bit more aggressive.
Cool. So like Tashi now said, is not every link's a pluggable link, right? So transponders still have a place in the world for various reasons. Sometimes the protocols predominantly coherent pluggables and stuff